Okay, welcome. So it was a really interesting session yesterday. I don't know if it's working. Maybe I don't need this. So it was a really good session, and we had a very hard time deciding who all to select to the finals. And we were like divided. We couldn't figure out, and eventually we decided to select all of you. So it was a very good poster session yesterday, and it was very hard for us to decide who not to select for the finals. So, so all of you would be presenting. Ensure that you stick to the time limit of 10 minutes because we are really, this is a very tight schedule because there are 8 presentations going to happen. And we start with Emily. Thank you.
Yeah, sure. So, hi. Let me begin my presentation on Siloso, which is a dialect adaptable reference engine to detect logic bugs in database systems. So first off, database systems are pretty common. They provide powerful and universal functionalities for data management, and many of them adopt the relational model and use structured query language as the primary language to describe and manipulate database systems. But because database systems are so commonly used in the development of software systems, any bugs or inconsistencies in them can have very large consequences. So our core goal at hand is to be able to detect logic bugs in relational database systems. Logic bugs refer to bugs that can cause an incorrect result to be returned for a given query evaluation. Take this SQL query for instance. If we were to evaluate this on MySQL, it will return an empty result set, which is contrary to our expectations. This is a logic bug that we have found using our system and reported to MySQL. And the developers have also verified this bug. But as you might imagine, trying to detect logic bugs in database systems can be a pretty challenging task because we effectively need a way to characterize the expected query result for a given query evaluation. This is also known as the test oracle problem, which falls into the realm of automated database systems testing. Here, we have a test case generator, which generates test cases that gets evaluated by the database system, and the test oracle takes as input this query result and validates the correctness of it. There have been various approaches to designing test case oracles, one of which is metamorphic test oracle. Here, we have an original query as well as a derived equivalent query, both of which obey some set of relations, and we expect that the result produced by the original query is also equivalent to the result produced by the derived query. One such example is ternary logic partitioning, short for TLP. At the bottom, we have our original query, where it produces one row if we were to evaluate it. To understand TLP using the perspective of the previous bug report, what we'll do at the top is that we'll generate 3 different partitioning queries based on SQL's 3-valued logic system. And we expect that the number of rows returned in each of those partitioning queries sum up to 1. If we were to evaluate this on MySQL, that is indeed the case, which also means that TLP can potentially ignore the bug report that we have found. It can ignore such classes of bugs where expressions get evaluated incorrectly in a systematic manner. There are various approaches to metamorphic test oracle designs, but many of them are partial. Another aspect of test oracle design is for the differential test oracles. Here, we directly compare the query execution result of 2 database systems. This was popularized in the 1998 paper from Microsoft Research. But we can also take this one step further and ask if we can compare the query execution result of a database with respect to a reference implementation that can fully model the semantics of the database system. There have been various works on this by Google, and the limitation of this is that it's specialized to a particular class of dialects, so it takes a lot of work to build a reference engine from scratch for another dialect. There's also a recent work just last year, SAMCON, where the authors tried to formally try to model the standard SQL specifications using Prolog. But such work also sidesteps the dialect problem because different database systems can have different underlying SQL implementation and do not necessarily conform to the standard SQL specs. Therefore, we might ask if there is a more general or shared reference that we can use that is applicable to different dialects. So, as a summary, these are some of the key challenges in automated database systems testing. First, we face the dialect problem, and as a result, many of the test oracles are mostly partial. Here is where our work comes in. We introduce Siloso, which is a test oracle to detect logic bugs in database systems. More than that, Siloso is also dialect adaptable, which means that given a test case, Siloso will execute a test case according to the semantics of the specified dialect, which is PostgreSQL in this case and MySQL in the previous case. In total, we integrated Siloso with popular test case generators like SQLAnswer and SQLsmith and found 27 bugs across 6 different database systems. So, as a database system, Siloso comprises 3 main components of query parsing, planning, and evaluation. So the first 2 steps are largely dialect agnostic, so I will focus more on the third step, which is query evaluation. So as a first step, we might want to ask how we can achieve dialect adaptable query execution with just one single reference engine. We might be very ambitious and try to model various aspects of the database system, but we argue that this is not necessary to detect logic bugs that arise from the incorrect implementation of database system semantics. Instead, we identified commonalities across various dialects and database systems and focused on modeling the key variabilities of a database system that affects its semantic correctness. Here, we implemented various functions, operators, aggregators, and types according to MySQL semantics. You can think of this as building blocks that can later be extended, composed, and reused across various dialects, say PostgreSQL, TiDB, and so on. For instance, suppose we were to evaluate this query. What we'll do during the query evaluation stage is that the query evaluator would interoperate with the dialect manager on the right to retrieve the dialect-specific implementation of the like operator, as well as rely on the dialect-specific type factory to interpret the type of the string value at the bottom. But you might also realize that this is not super feasible because there's a ton of functions and operators in just MySQL alone. This brings us to our second insight, where we delegate the evaluation of unimplemented functions and operators to the actual database system. Take this for example. Suppose our system doesn't support the SoundX function. What we will do during the query evaluation stage is that the query evaluator would notify some observer, which will then delegate the evaluation of this SoundX function with some concrete arguments to the actual database instance. Finally, to fully realize the goal of modeling the semantics of a database system, we also try to model ambiguous queries in our system. For this particular query, suppose we ignore the limit clause, then we expect that selecting C0 from T0 gives us 3 rows in total. So if we include a limit clause without an order by, then it's possible that any of these 3 rows is a correct result. So we modeled this by returning the full list of possible results. And in the future, we could further extend this using ideas from abstract interpretation, where we also model indeterminate values. So we evaluated Siloso extensively and found about 27 bugs across 6 different database systems, all of which are unique and have been verified by the respective database system developers, a proportion of which is 13, have also been fixed in .db. So just now, we have just covered the development of Siloso as a dialect-adaptable reference engine and demonstrated its effectiveness in being able to detect many bugs that are found. So as a second step to the evaluation, we also want to compare Siloso with existing techniques. And this is twofold. Firstly, we want to know if we can also detect bugs that are detectable by existing techniques. And second, we want to see if Siloso can uncover new bugs. In tandem, we're also conducting a motivational study to study the features in bug-inducing test cases and how SQL features differ across database systems. This can further enrich our understanding in the development of Siloso. For the next step, we also want to see how we can further reduce the amount of implementation effort needed to extend Siloso to a different dialect. For instance, we can go for an automated scaffolding approach which generates dialect-specific components together with test suites for developers to validate the correctness of their implementation. Finally, the query parsing stage at the moment uses a general catch-all parser. So we want to see whether there is a suitable intermediate representation to use so that we can also parse the query in a dialect-adaptable manner. So that wraps up my talk. So in my talk, we focused on trying to identify how bug-inducing test cases look like, and in tandem with that, we used the insight to inform the development of Siloso and evaluated it extensively across 6 different database systems. So finally, I would like to thank my advisor as well as the respective database system developers for their time and effort in fixing the bugs that we have introduced. Thanks.
We can take a quick question. In the meanwhile, can the second speaker set up their machine?
So can you say what's a catch-all parser? What do you mean by that?
Right, so currently we are using, so our system was developed in Java, so currently we're using JSQL parser, and JSQL parser is an open source project that is meant to be a highly flexible parser that can parse various dialects like from CockroachDB, PostgreSQL, MySQL, and so on. But of course, there's limitations to using such a general parser because there's always instances where queries from some rare dialects cannot be parsed. So in this case, this is a general parser. And in the future, we want to see how we can extend it to use a dialect-adaptable parser that can effectively and correctly parse different dialects.
Okay.
Yeah.
So did you encounter a lot of cases where it wouldn't parse some rare features?
So far, there have only been a few cases. For example, in CockroachDB, if we were to use a join clause, it's allowed to specify, say, hash join, merge join, or so on in CockroachDB, which is an optimization feature that informs the database system how to evaluate the query. And to mitigate this, currently we also leverage the observer feature that we have implemented because we recognize that such clauses are not relevant to the correctness of the database of the query evaluation. As a result, before the parsing stage, we rely on the observer to remove such instances of illegal query syntax.
Okay.
Yeah.
Thanks.
Thanks.
Thank you. So maybe you now the second speaker.
Hello? Okay. So our work today is to formally verify the Graham scan algorithm. As you can see that first we introduce the definition of convex hull, which is in our case a minimal polygon containing all the given points, which is planar points. And the general definition, as the Wikipedia has shown, is that it is also the smallest convex set. So geometrically, this is the minimal polygon. And why we want to verify this, or why we choose the Graham scan algorithm, there are several reasons. Firstly, it's wide usage in industries like computer graphics and robotics. And it's also have error-prone implementations in programs where in edge cases, we might solve some false convex hulls, and also the complexity in existing formal proofs, which are embedded with some topological properties and hard for human to understand. So the Graham scans algorithm is a two-step approach. Firstly, we select the leftmost point, and sort all the points in polyangle order, as you can see in the left picture here. And the second step is to maintain a stack and continuously check the top 3 points is left turning or not. And we form the final hole through this simple stack incrementation process. And we want to verify the final correctness of our algorithm is that it always generates a convex hull, which is divided in 2 sub-properties. The final hull contains all points, which are given points, and it is itself a convex polygon. As we can see that these properties are all formalized in ROC-proof assistant and with precondition sort here. To make the proof easier, we propose 2 equivalent definitions for these 2 subproperties, like we use in the left to or the edges or triangulation step to check if a point is inside this hole or not. Let's take an example to show how the proof can be difficult in some cases. For example, the point in triangle inclusion is a common used property in our proof process. It is saying that if B is inside the large triangle PAC, then the splitted little triangle PBC is covered by the larger triangle. This can be trivial from human geometry intuition, but for proof assistant, if B sits on the edges or vertices of the triangle, which is some corner cases, ROC's tachyneer will not be able to reach any useful conclusions. Like we have to manually write proof like asserting dot product or cross product relations. And this is very effort taking. Each subcase may cost over 1,000 lines of code. So we have a novel method to relieve this burden. And let's him to introduce.
Okay. And to save manual labors, we design a system to generate the ROC proof automatically. And let's introduce the transformation. Transformation is a coordinate system transformation to create a new coordinate system. And why we need this transformation is because it is easier for LLMs to generate proof with higher accuracy, and it can lower the difficulty of LLM's reasoning. Here is an example for the lemma point in triangle collinear mid 1, 1. You can see here from the left to the right is a transformation. And choosing a new origin and a new x-axis direction is a key point in this transformation, and we use LLMs to make these decisions. And you can see here, the LLMs choose B becomes the new origin, and vector BC becomes the new x-axis direction. We also create some lemmas to support these transformations. The left one is the collinear ambit chance, and the right one is the CCW. Also, we created some templates, and a template for AI is a defined structure of format to guide the model to generate a specific types of response with restriction. Here is our workflow overview. You can see here we designed several prompts to make AI to generate a proper generation. In our step 1, we let LLMs to translate ROC statements into natural language statements. Here is an example. You can see the ROC statement translates into the natural one. In the step 2, we generate the natural language proof by using the natural language statement. And in the natural language statements, you can see that the point B, the origin with coordinates 0, 0, and it can greatly reduce the difficulty in our proof. In the step 3, we generate the rock proof with template rock proof. And you can see here, this is an example of the rock proof, and it can be verified in a rock. So here is our results. We have 10 properties to prove in total, and if we give 10 attempts for each properties, and they can be all proven. And the result is quite promising, and here is our analysis and insight. IAM's errors is always the incorrect usage of rock syntax and the theorems. Also, it may be because of the insufficient rock training data while training the LLMs. To enhance the LLM's abilities, we can offer templates and examples to restrict the LLMs to formalize it. And we can enable AI to reason with natural language. Thank you.
We can take questions. The third speaker can start.
I'll ask a quick question. So this work, you generate the proofs by large language model. Can the large language model use to generate the lemmas?
Yeah, so in this question, we are proving some properties needed by the final proof. And for the sub-goals, we have these lemmas and its transformation form are all generated by LLM. So by composing these sub-properties, which are all generated by LLM, we can see only some top lemmas, like the 10 properties we have to written by hand, and all proof steps and sub lemmas can be or automatically generated by LLM.
All right, thanks.
Okay, should I start? Yeah. All right, good morning everyone. I'll be presenting my work on concurrency testing approach for detecting isolation level bugs in database management systems. So first, I'm going to talk about the brief problem overview first. We are usually a little bit familiar with the notion of serializability, but I'll have to recontextualize it into the isolation level definition of what serializability is. So modern database management systems, they offer this performance guarantee that they can perform concurrent transactions, and then they can ensure the correctness of these transactions. Transactions consist of read, write, begin, commit, and so on, and any combination of those. So they offer correct execution under complex concurrent transaction workloads, and the way they ensure the correctness or the interface of the correctness is these things we call isolation level. So isolation level, for example, with the strictest being serializability or serializable, and it would be the rule that even if transactions are concurrently executed, then each transaction will behave, and we can observe that each transaction will behave as if they were executed serially and independently. Adia, Liskov, and O'Neill in their 2000 paper formalized the isolation level definitions. So there are weaker isolation levels than serializability because sometimes serializability is too slow and databases offer weaker isolation levels. That's why we call it isolation levels. And some of them maybe you're familiar with is repeatable read. So repeatable read will entail that if you have a transaction that reads the same object twice in the same transaction, then the object that is being read should return the exact same result. Sorry, this is not presenter view. Okay. So the term ADIA history itself is not that complicated, in that ADIA history is basically presenting a dependency graph. So we have transactions, and then transactions can have edges to another transaction if they have like read-write or write-read dependency, whereby maybe I write this transaction writes a particular version of an object, and then another transaction reads that version of the object. So just a brief on the detail. So the big question is that now they're offering this isolation level guarantees. How do we know if the DBMS actually obey the isolation level it claims to enforce? One question might be, can we not simply observe the ADIA history that we got and then see if there's a cycle on it, and then say that, oh, if there's a cycle, it's definitely a serializability bug, for example. Or maybe there's different kind of cycles that are allowed in weaker level of isolation levels, but generally speaking, can we just not look at the ADIA history and see what's going on? Well, the problem is that ADIA history is a conceptual abstract theory of what isolation level is, but in reality, we don't have access to such ADIA histories. So what people usually do, due to the sheer complexity of the database management systems, is existing approaches. I think one of the presenters just now are also doing something like this. They test database systems correctness in general, maybe not specific to isolation level, but they use some tool to generate queries, and then they, in the context of isolation level, they usually bombard the database with concurrent transaction workloads. Other approaches is this Cobra and Viper. So they verify the exponential amount of possible ADIA histories that is generated from an observed black box point of view, and then for each of these, they would want to make sure that in this execution, for all of the possible commit ordering, there is no commit ordering that satisfy the isolation level that the database guarantee, and then they would say that it's a bug. The other more clever method is L. So here I have an example of what L does. This will be important because L is the system that we're comparing against. So L restricts the database to only database that supports atomic list append operations. And this way, they can try to recover the ADIA history that they want to, or the dependency graph, and verify quickly. For example, here they have a serializability violation found in PostgreSQL 12.3. And what happened is that the syntax is there is a transaction here, and there's a transaction here. This transaction reads the object 1799, the object with ID 1799, and returns nil. So it means that the object 1799 has not been written to yet. And then another transaction comes in and writes append 17992. So then we can infer that there is a read-write dependency here. So this transaction reads something that you haven't written. So this transaction must have happened before the transaction on the above. But if you'll follow this exact same logic to this transaction, then we'll see that there's another read-write transaction going to the opposite edge, and therefore this is not serializable because we have a cycle. So the thing is, this is sort of like concurrency testing, whereby there is some object being accessed, and then it's being read, it's being written, but it's more on the abstract level, in that database objects are far more complicated than simple memory locations. So what do we generally want to see when we do concurrency testing? And it is not really trying to bombard the input itself, the workload input itself, but rather we really want to see different interleavings of schedule, maybe using the same workload or otherwise. So it's not working. Okay, so concurrency testing methods usually do this by using a preemptive scheduler, and they preempt some. They have some events that can be executed at a point in time, and they preempt something, and then they instead execute other events, and so on. So they can have like different schedules in each cycle. So here I introduced the ISO-FUZ framework, which is a novel gray box DBMS testing framework consisting of an instrumentation library. So we have libraries that have hooks that you can put into your database. And then we have a transaction scheduler overrider. Once you're, I'll give you an example. If you have a database systems and you use the isofast instrumentation methods and then recompile those your database systems into the instrumented database system, you simply then can run the database systems in your isofast environment, and then it will have a fixed amount of workload that will then test it, and then isofast will take control of the concurrency control module, and then of the database, and then it would forcibly force the database to execute different transactions, different interleavings on transactions, and thus producing different dependency graphs. Because we have access to those particular instrumentation points, we can also log when does a read happen, when does a write happen, when does a commit happen, and when does a begin happen. So this means we can recover the full ADIA dependency graph without ADIA history, without any guessing on what had happened in the actual database, because we can actually know what the database executes. So we provide a methodology to correctly place instrumentation points such that any bug reported is sound. So we have rules for where you should put your log commit, your write commit, read commit, and begin commit. And with these rules, it's pretty simple if you are the database developers to know where to put these instrumentation points. So once we have these rules that covers all the read, write, read, and write edges, we can guarantee that the dependency serialization graph seen in the produced by isofast is indeed what happened. So no spurious or missing dependencies, and thus any bug reported then is will be sound. I'll skip this one because of time. So going to the evaluation part, how effective it is against the state-of-the-art tester, we are barely coming close in terms of the number of transactions we need to surface a violation. So if we compare to L, we are slightly lower, so we need only 31.20 transactions in average compared to L's 34.43. The good news is this number, our result never gets higher than L's. And even better news is that our method works for any database object, because we are instrumenting on the read-write level and on the really low level of the database. We don't really care of the semantics of SQL, the workload, and whatnot. So you can use this to test any sort of database that have this transactional property or guarantee. And then regardless of what the workload is, you can use the normal daily workload. It can be tested using, it can be tested and verified using our method. What's really nice also is that we have polynomial time verification compared to the other systems who have to infer what dependency graph happened and then confirm that, and then verify each of these dependency graph. We actually have the dependency graph, so we simply can try to find a cycle inside. We also easily replicate known bugs with a 30% bug hit rate after instrumentation. Simply with random walk, we try to find known bugs, concurrency bugs in MySQL forum, and we try to replicate it, and it works really well. It surfaces most of the time compared to what people discuss in the forum, whereby they cannot find the bug, they have to put like manual delays to actually see the bug. And turns out the instrumentation points inserted is also pretty low, not that much compared to other, I don't have the numbers, compared to other, some sort of white box method or instrumentation point method. We only have 23 instrumentation points for MySQL and 2 instrumentation points for SQLite. Yeah. So in conclusion, we have a somewhat superior effectiveness in detecting subtle IL violations, and implementing these instrumentation points is reasonably easy, and yeah, we can definitely improve performance optimization for the verification for our fuzzing method, because our fuzzing is pretty slow compared to other systems currently. Yeah, thank you.
We can take a quick question, and the next speaker I'll ask.
Can the instrumentation be done automatically?
Yeah, so I didn't show it there, but for MySQL, we actually did automatic instrumentation. So for SQLite, sorry, because SQLite is a pretty simple database that is pretty self-contained, and we can control we instrument it automatically using normal concurrency testing approach, whereby we use E9 patch to rewrite the binary, and then we insert preemption points on memory read, memory write. But it's a bit too granular, but it works. Yeah, so it can be done automatically, but in general, for the bigger databases, we try doing that. It ends up having like lots and lots of deadlocks everywhere, so we cannot really do that. So yeah.
Okay, so hi everyone, I'm Yunbo Ni. Today I'm excited to present our work, LegoFast Interleaving Large Language Models for Compile Testing, conducted in collaboration with my advisors, Professor Ming-Jue Pan and Chaohua Li. Currently, we have several amazing LM-based testing tools, such as FastForward and YFox. Those tools have demonstrated great potential in using large language models for testing. However, they're not so effective for testing compilers. If we take a closer look at their reported bugs, two major issues appear. The first is the long complexity of the generated program. For example, FastForward only discovered 8 front-end bugs in GCC. The second is the limited symptoms. The 2 bugs found by YFox were both simple crash cases. This raises a key question. Can today's LM-driven testing tools really hold up in the wild, like in a CI pipeline? There are 2 major challenges to achieving this. First, the typical workflow of these tools feeds code documents or like small snippets into an LM and asks it to generate a single test case. To produce millions of test cases, we have to curate the LM millions of times, which quickly becomes so expensive. Second, the generated programs are often of low quality. LM tends to produce code with syntax or semantic errors, and even when compiles, the program are usually too simple to trigger deep or meaningful compiler bugs. Thus, simply prompting LMs doesn't mean effective fuzzing. So why aren't they enough for compiler testing? First, LMs are too slow. Tools like FastForward can only generate about 16,000 programs today, while traditional fuzzers can easily produce millions in one day, making large effective fuzzing extremely inefficient. Second, the generated code is often too valid or like too simple. For example, FastForward's valid rate is only about 37%, and many samples either fail to compile or crash right away, like the buggy example shown here. Invalid programs get rejected early and rarely reach deeper compile paths like optimizations or code generations. Finally, LMs struggle on real compilers. Tools like YFox cannot map high-level reasoning to low-level implementations. To address these issues, we designed LegoFast. The core idea is very simple. We decouple the LM usage into 2 stages. An offline stage that builds a reusable code database using LM, and the online stage that synthesizes large value programs without curing the LM gain. On the left, the offline stage starts with code from GitHub, lets the LM generate diverse snippets with those examples, and then validates and profiles each one. On the right, the online stage uses these functions as Lego blocks, connecting them through function calls or global variables. With each iteration, the program grows more complex and realistic. In short, the offline stage ensures real and valid code generation while the online stage builds deep and interconnected programs at minimal cost without curing LMs. Now let's take a closer look at the offline stage. We'll aim to generate real-world code with real complexity. Previous LM-based testing tools are often feed models with simple context, like standard documents or small toy snippets, which fail to reflect how real compilers behave in practice. Here, we instead provide real-world code and meaningful context, so the LM can reason about the actual program logic and the true semantics, and transfer the code snippets into compile and realistic functions. For example, we use a real code from ACC. Then our prompts ask the LM to convert these programs into a unified compilable format while preserving their original semantics. This task doesn't require the model to write a new code from scratch, but rather to understand, reason, and restructure the existing real-world code, which perfectly fits the strengths of the large language models. Here it expands the complex struct parameter and replace external functions with functions from STD, which traditional tools find very difficult to do. The key takeaway here is LLM truly understand the code semantics. They can reason, transform, and complete synapse, laying a strong foundation for our offline database. After generating these real-world functions, the next step in the offline stage is to make sure they are both valid and reusable, while maximize the semantics for the testing. In total, LEGO Fast construct a database of over 500,000 valid functions. How do we construct it? Let's take the same example as before. There's a potential runtime overflow here when writing the body array. To avoid this UB, we automatically validate and profile the LLM transform program using multiple compiler toolchains, like sanitizers, like ASIN here. Functions that fail any of these checks are discarded. The remaining valid ones are then profiled to get their I/O values and runtime profiles. For example, we know that len equals to 1 and n equals to 2 at the beginning. Now let's move to the online stage, which focuses on building dependencies to increase the complexity. LEGO Fast reuses the validated functions from the database, and first it generates a driver program, a seed with the main function here. It calculates and produces a checksum for later differential testing. Then it builds dependencies among them through function calls and global variables. Once the driver functions and dependencies are ready, we can directly start fuzzing on compilers like GCC and LLM, completed without any LLM involvement. Here's how LEGO Fast performs iterative synthesis using what we call function breaks. For example, we want to synthesize for function to the buffer write mentioned before. How do we achieve that? Each function in the database comes with profiling info, as we mentioned before. For example, for takes input 1 and output 2. Also, for buffer write, we know that alloc equals to 2, the same as the output of the for. So we start to replace alloc with for. The function for also requires something as the input. So here we got the variable len with the same value as the input. As a result, the synthesizer simply replaces alloc with f, with for with the length. We also add the function call to the driver function here to calculate the checksum. This links the two functions through data dependency, keeping the program valid while making it more complex. The second way LEGO Fast links pieces is with global variables. We have prepared a list of random global variables at first. For example, the g with the value 1 here. Our profiling shows that at this site, len equals to 1. So we simply replace the use of len with g. Same as before, we use g to mutate the checksum as well. Together with function call insertion, the global sharing enables LEGO Fast to build large, meaningful test programs. And finally, we print and compare the checksum and different optimization levels to find if there exists any compiler bugs. Finally, let's see how well LEGO Fast actually works in practice. So far, LEGO Fast has found 66 bugs, and 56 have already been fixed by compiler maintainers. What's notable here is almost half of them are miscompilations, subtle logic errors that many existing tools completely miss. Some of these bugs are quite important. One of them had existed for over 20 years, and its discovery even led to an update in the SMT GCC tool. You can see the maintainers' reaction on the right. They were surprised that the bug hadn't been caught earlier. Overall, LEGO Fast can uncover a wide range of issues, from crashes to deep optimization bugs, demonstrating that it's not just a theoretical, it really works end-to-end. Finally, we compare LEGO Fast with several state-of-the-art tools, including Serial, FastWall, and Firefox. In terms of bug fighting, neither FastWall nor Firefox was able to discover any miscompilation bugs. While LEGO Fast consistently uncover both crashes and deeper logic issues. For cryogenic speed, LEGO Fast achieved over 50,000 lines of code than the other tools. And for the generation speed, we ran about 146 times faster than those baselines. The example on the left shows one of our synthesized programs. It forms a long dependent chain built through multiple iterations, which helps expose complex compiler behaviors that many other tools simply miss. To wrap up, LEGO Fast opens up several promising directions for future work. First, we can explore alternative printing methods. Second, we plan to incorporate more sources code snips. Third, we can go beyond function-level synthesis. And finally, beyond C compiler testing. This brick-by-brick idea doesn't just stop at compilers. It points to a broader future for LLM-driven program synthesis and automated testing. To summarize, LEGO Fast is a powerful and cost-effective LLM-based framework for compiler testing. It combines two stages, an offline stage that builds real and reviewable complexity, and the online stage that is fast, cheap, and completed LLM-free. In real-world testing, LEGO Fast has already found multiple bugs, 66 bugs, with 40 with 56 already confirmed freaks in GCC and VM. More importantly, it introduced a new paradigm for LM-based testing, one that is easy to understand and highly effective in practice. So thank you for listening, and I'm happy to take any questions here. Oh, I see.
What kind of miscommunication bugs did you find? What did you generate as well?
Well, you mean the miscalculations? Yeah, we found a lot of miscalculation across different components like the middle end optimization parts and in the back end crashes. So you can find like maybe some of the bugs would produce different outputs at different levels, like you produce 1 at O1 and maybe 2 at O2 and O3. Yeah.
What caused these differences? It's just optimization bugs?
Yeah, because they produce like different IR in LVM, and the transformation is wrong due to some of the. Yeah. Oh, thank you.
Hello, my name is David Anthony Fields, and I'm here to talk to you today about automata visualization for validation and verification. This is joint work with my advisor, Marco Morazan from Seton Hall University. In a typical formal languages and automata theory course, students are introduced to various computational models. However, a common problem that students face is understanding nondeterminism. And without a solid grasp of nondeterminism, they then fail to understand the machine's operational semantics, and they fail to understand why the machine can reject a word without fully consuming it. So we think that visualization tools can help. We wanted our visualization tool to dynamically simulate the execution of finite state automata, so DFAs, NDFAs, PDAs, Turing machines, and multi-tape Turing machines. We also wanted to visualize all possible computations that these machines can have, regardless if the word is accepted or rejected. And we also wanted to support the validation and verification process for these machines. So instead of me telling you how we plan on doing this, why don't I show you instead? So here we have a student-designed program for the NDFA that recognizes the language of A clean E plus, union AB clean E star, union empty. We have this student has provided with us the state documentation, so they've informally defined their invariant predicates, and we have the implementation of the machine found on lines 10 through 16. The unit tests for the machine are found here, and then we have the implementation of these invariant predicates at the bottom. So we can take these, we can take the implementation of the machine and these invariant predicates and then run them within a tool. And we can then step through this machine's execution in a stepwise manner. That's embarrassing. So the input word here is A followed by 4 Bs. The visualization is split into 3 main parts: the main visualization graphic at the top, the informative messages in the middle, and the instructions at the bottom. So here we show all computations that the machine can have by highlighting the separate edges that the machine uses. If an edge is highlighted in pink, then it is a part of a rejecting computation. And then if it's highlighted in green, then it is a part of a an accepting computation. Additionally, we visualize the values of the invariant predicates that the student provides as input. So here, it's highlighted in green as S's invariant predicate holds. Now, if we step forward in this visualization, we now see that 2 arrows are highlighted. One is a dark green, letting us know that this is an accepting computation, and the other one is violet, letting us know that this computation has also been rejected. And also, B's invariant predicate is highlighted in red. This lets us know that it's either the implementation of the invariant is wrong or the design of the machine is wrong. We can then step through the rest of this word, and we see that B's invariant predicate is failed for the entirety. And now that we're at the end of the visualization, we get an additional message letting us know that this word has been accepted by the machine. So the student can then go back look at the implementation of B's invariant predicate, where they then see that they have a bug. Instead of them taking the rest of the consumed input, they put the entire consumed input to see if every element is a B. So we can correct that bug, rerun our program, and then we can rerun the visualization tool. And now we can see that B's invariant predicate is now green, letting us know that they've successfully debugged their invariant predicate. We can also help students understand non-determinism by optionally adding the dead state. So first, I'm going to show you what the tool would do for the NDFA, and when we give it the word ABB, ABB. So here we have, we can see that our color legend at the bottom has changed. There's no green. Instead, there's just orange and pink. Orange denotes another rejecting computation that's actively being followed in the informative messages. So we can see that we're from S, we take the A into B, and then we stay at state B and we continue. But then when we read the A, we get into an informative message just letting us know that all computations don't consume the entire word. And a student who is just learning about non-determinism may be confused by this, as they've just learned that DFAs have to consume the entire word before accepting or rejecting. But now this NDFA has only consumed half of it and has rejected the word. So the student can then use a keyword argument to add the dead state to better help them understand why the machine has rejected this word. So now we can follow along. All transitions to the dead state are denoted by dashed edges, as you can see, or as dotted edges, as you can see here. So as we step through the execution of the machine, we can see that the computation at state F has transitioned to the dead state as it consumes the A. The computation in state A transitions to the dead state as we consume the first B. And the computation at state B transitions to the dead state after consuming the second A. Now the student can clearly understand why the machine has rejected after consuming the trying to consume the second A, as now all computations are within a dead state. We can then continue to finish consuming the rest of the word. We get the same message, we get a different message letting us know that all computations end in a non-final state and that the machine rejects. Now for machines that semi-decide languages such as PDAs and Turing machines, we allow them to partially simulate the word by introducing a user adjustable cutoff threshold. Let me run this. So the goal behind this user adjustable cutoff threshold was we didn't want the visualization tool to run into an infinite computation. So instead we allow the user to partially visualize this. So here I can run a Turing machine for the language A to the N, B to the N, C to the N. And I've set the user adjustable cutoff threshold to be 16. So we can step through the execution of this machine, and there's two computations that we're following, one in pink and one in green. And I've also provided the state invariant predicates for all of the states. So as we step through, we see that the invariant predicates hold, and we are now and now we can see that these two computations have diverged. One transitions to state H, and the other one transitions to state F. So as we continue to step through the execution, we see that now one of the nodes is colored in either green or red. This is colored in gold to denote that this computation has cut off here. And we also see that the machine has accepted the word at state Y. So now that you've gotten a feel for the visualization tool that we provide in FSM, let's compare and contrast with some related work. JFlap is a popular program that, like FSM and our visualization tool, highlights all possible computations. However, the user must manually construct the transition diagram. It also provides no informative messages during the visualization. And there's also no validation support for the machines. Also, Automata Tutor, like FSM, provides immediate feedback on the design of their machines. However, it does not trace all possible computations, which can lead to students believing that some non-deterministic machines are deterministic since we're only following one computation at a time. It also, like JFlap, does not support the validation process for machines. So to conclude, I present a novel visualization tool that traces all possible computations through the use of color, coding, edges, and nodes. We also support and visualize the validation process to help students with verifying their machines. And for machines that semi-decide languages, we have a user adjustable cutoff threshold so they can partially visualize their machines while not having to worry about running into an infinite computation. Our future work includes conducting a user study to gauge students' experiences in using the tool. And thank you for your attention. Do you have any questions?
Great. Thanks for the demo. It's really fun. I just saw there are some different color words called accept traced, reject traced, or there are some notes there. Can you help me understand what does it mean?
So by the accepting trace, this is just an accepting computation. The darker green means this computation directly correlates to the informative messages. The lighter green would denote another accepting computation that the machine can have. And then the pink one would denote just a rejecting computation.
I see. There are just the notes how to read the diagram. Is it? There are the notes how to read the diagram, how to read the automata.
Yes. So in the running of the course, the students are introduced to the machines and how to read the diagram. The starting state will be highlighted, or they're told that the starting state is highlighted in, it's colored in green. The final states are double circled, and all of the edges denote a transition and a transition relation. And we then provide in the visualization tool a color legend at the bottom to further help them understand what each of the colors mean.
Right. Thanks.
I think.
Okay. Okay. Okay, so hi everyone, my name is Polina and I'm a PhD from Politecnico di Milano, and I'm doing my PhD actually in design, which is not really classical computer science degree, and especially in this very engineering environment. I know that it's very different, and I know that my work especially differs from other participants of this part. However, I think it's very important to deliver a couple of ideas that I do in my research to the engineers, because that's the reason I'm doing my research. So my PhD research is focused on how to design and develop secure but also accessible personal health data solutions. And the central motivation for my research begins with a simple but yet very profound statement, which is we generate vast amounts of personal health data, but we have really little control over that. This data is typically managed by centralized systems, which creates a lot of vulnerabilities and leave users, especially with very limited control over their most private and sensitive information. So as one of the solutions that can be proposed is the blockchain technology. It offers very powerful solution for data sovereignty due to its immutability characteristics, as well as the implementation characteristics with the smart contracts. But the problem with the blockchain that it's very complicated to use for the end users, and most of the solutions that you can find right now on the market are developed exclusively by the engineers, which is cool, technically speaking, but yet very complicated for the final users. Moreover, very often designers and engineers and also researchers don't really communicate between each other, so their findings and their ideas are very siloed and not being shared. So this is where my research comes. In this research, I'm trying to solve different issues, mostly for designers, yet still also for the developers. And that's why I'm trying to work on a different projects. There is the main project, which is the project number one, which is a smart fidget toy, which I will describe a little bit later in more details. And there are two more other projects that came from the ideas related to the project number one that are exclusively sources for designers and developers to take care, to have a look while developing their blockchain-based or not only blockchain-based products. So as I'm coming from the design department, matter of fact to say is that the research methodologies applied in my research are also from the design industry. So there are two types of them that I'm using: research through design and research for design. In the simpler words, that means that research through design is actually act of prototyping and making things. And this is where a lot of technical parts of my research come from. And for design is essentially developing different theoretical frameworks for them. The important part here also to mention is that the research through design component is the reason, as I mentioned also in the previous slide, for developing research for design. So the central contribution of my research is a smart fidget toy, which is essentially, in my work, is experimental probe, where we were trying to develop a solution for health, but not talking directly about health, since I'm not a health practitioner, but at the same time also to see all of the developmental issues that are related into the embedment of blockchain into the variables. So what I did here was essentially to develop the entire prototype, both the hardware, the software on the device, and as well as the web application. To do all of that, I was asking a lot of the users. So while I was implementing the technologies, the source of my decisions were always the users. When we just started working on that project, at the very first moment, we decided to ask them actually what they're interested in what type of the data collection they're interested, and also what kinds of interactions they might be willing to engage. And through each of those steps later on, we were taking every little decision on the shape and design of the fidget toy. A very easy example to mention is how to communicate the data from the device to the actual blockchain smart contract. For example, we decided to do it through the serial web communication to first of all force users to do a little bit more of the actions and to keep their devices charged, because many of them mentioned that they would forget probably to charge it, as well as still it provides a little bit more security than the wireless solutions. While the process of building CipherPal generated wealth of knowledge, it additionally sparked the development of the two other projects mentioned before, which is the design toolkit, which is essentially a digital canvas which designers or developers can fill in as in a workshop-like format and see the actual issues their products have. Or the second product is on the right, which is a web-free design guidelines, which are accessible for, in terms of the language, to anyone who works with the web-free development. It's very much targeted towards developers, and we divided it into simplified tasks, which are the categories of the user actions, and then also it's divided on the horizontal way towards the level of the implementation the developer wishes to achieve. And inside of each cell, they can find different suggestions on what to do and what not to do in their products. And this brings me to the final and most important phase of my research, where we were trying to synthesize on all of the contributions we did. So we took the probe from the project number 1, which is a smart fidget toy, and we evaluated it with the experts applying the web-free design guidelines. Then we evaluated it also professionally using the user acceptance toolkit, and then we also gave the probes to 8 users for 3 days in their houses. And we separately analyzed the data from each of the strands, and then we tried to find the contradictions and overlaps of each one. So what did we find? The first very major insight was what I call the blockchain paradox. So users conceptually really liked the idea, but when practically they started to interact with the platform and with the device, the friction that it was bringing, especially the interaction with the crypto wallet, was hindering all of the usability and was bringing them just too much of the frustration. Though, matter of fact, this brings to another finding, which is the productive friction. Because when they're being asked, okay, but when you were trying to confirm the transaction or when you had to connect your device, were you still doing it just manually or not? Most of them claim that, yes, it was annoying, but that made them think a little bit more about safety of their data. And matter of fact, most of them claim that if being a teenager, they still had an ability to choose between the blockchain-based solutions or common centralized systems, they most likely would have chosen the blockchain-based solution since it gives them more privacy, especially in the implementation that we did. So, and my research therefore gives several implications for all the free stakeholders. For the designers, we provide a huge sets of the sources how to work with the different emerging technologies, especially with the blockchain. For the web-free developers, we're trying to emphasize especially the necessity of talking to the designers. And if they don't talk to the designers, at least maybe to consider furthermore the usability experience of very complex technologies. And for the researchers, we propose different multi-framework solutions on how to assess very complex social technical issues. So to conclude, my research highlights once again that When it comes to the very sensitive domains, the research must move beyond a simple technical implementation and must be considered from all of the parts, the technical and social aspects. Then the success really requires a lot of human assessment and a lot of user involvement. If that's not the case, then the probability of the product being actually used is very low, even though it might be technologically something completely new. And still the balance between the complexity and the user experience, user centricity, is not achieved just by one solution, but it needs multiple points of view. So thank you very much, and I'm happy to answer any of your questions you might have. And I must acknowledge all of the sponsors that helped me to arrive here, ACMW with the Google Scholarship, and the research was also supported with the funds from the Fitbit. Thank you very much.
We can have one quick question. So did you do some user studies?
Yeah, most of the things was the user studies. So we were trying to develop something while every time conducting user studies. The amount we conducted at the very beginning, focus groups and anonymous surveys, just to understand the preferences. Then we developed the wireframes, which we user tested with 7 users. Then we developed the mid-fidelity prototype, which looked essentially like this. So it was a little bit ugly also, but it was working. And the blockchain component was working still, but it was conducted in the lab settings. So still users were kind of assessed by the researcher, and the researcher was always there to help. And the final user study was 8 users for 3 days when we gave them the newer version of the device to their houses.
And what was the size of the group?
It's this.
8 people.
8 people.